Hey everyone! Today we're going to slow things down a bit and explore a hidden, honestly almost invisible aspect of the everyday materials that literally shape our world. In this explainer, we're zeroing in on the silent engineering that makes modern life possible, specifically the chemistry of plastics. But hey, don't worry, this absolutely isn't some stressful chemistry lecture. It's really just a gentle journey into how the microscopic world dictates the macroscopic objects we touch, use, and rely on every single day.
So I want you to visualize something for a second. Picture a standard plastic water bottle left sitting in a scorching hot car in the middle of July. When you finally get back to it, it's warped, it's squishy, and totally melted out of shape, right? Now contrast that with a plastic spatula resting right on the edge of a hot frying pan, or even the sturdy plastic handle of a boiling kettle. They're experiencing intense heat, yet they don't melt at all. Sure, if exposed to enough heat for long enough, they might char or burn, but they're never going to turn into a puddle of goo. Why is that? How can two completely different things, both just called plastic, react so totally differently to heat?
Okay, let's dive into this by starting with the bare basics. All of these materials belong to a super broad family of polymers, and they're characterized by a property called plasticity. Plasticity is simply the ability to undergo permanent deformation when subjected to stress or heat. Put simply, it means the material can be molded into a specific shape using heat, pressure, and, sometimes a catalyst. This moldability is exactly why plastics are so essential to modern engineering. They basically give us the freedom to create almost any shape imaginable. But once that shape is formed, different plastics take very, very different paths.
And that brings us to a huge crossroads in material science. The plastics we use fall roughly into two categories. On one side, we have thermoplastics. These are the water bottles of the world. They soften when you heat them up, they get rigid when they cool down, and crucially, this process is totally reversible. You can reheat and reshape them over and over again. On the other side, we have thermosetting plastics. Now, these are your spatulas and kettle handles. Once they're heated and molded into their final shape, they become permanently hard. They don't soften on reheating. In fact, if you just keep heating a thermosetting plastic, it'll simply decompose or burn. It cannot be melted down and reshaped.
To figure out why this happens, we have to look slightly deeper. The macroscopic behaviors we see in our kitchens, the melting versus the burning, are entirely dictated by microscopic structures. It all really comes down to the architecture of the molecules inside the material. While thermoplastics are made of these long, distinct, linear chains that can easily slide past each other when they get warmed up, thermosetting plastics are built entirely differently.
Let's actually break down how these permanent plastics are born. The thermosetting process happens in three core steps. First, there's a chemical reaction called condensation polymerization. So instead of forming separate, independent strings, like a pile of loose yarn, the molecules start linking across to one another. This forms massive, three-dimensional networks. Finally, through the application of heat and pressure, the material achieves a permanent setting. Once that chemical reaction completes, the structure is locked in forever.
Now, I don't want you to stress over the chemical equations here. There is absolutely no test at the end of this. Instead, just focus on the visual pattern of the structure. Notice how every single part is physically bound to the parts around it. Left, right, up, and down. This isn't a pile of loose spaghetti. It's much more like a rigid, interconnected chain-link fence.
So the crucial takeaway here is this invisible web. Those connections you're seeing are strong covalent bonds, because the entire material essentially becomes one giant, heavily cross-linked molecule. There's literally no room for the parts to slide past one another when heat is applied. The bonds retain their strength. This 3D web is exactly why thermosetting plastics retain their structure and remain completely locked in place. Heat simply cannot overcome those strong covalent bonds without destroying the molecule entirely.
Now, this invisible chemical web might seem like some modern marvel, but the breakthrough actually happened over a century ago. The year was 1909. This was a time of incredibly rapid industrialization, and engineers were desperately hunting for new materials that could handle the emerging demands of high heat and electricity. A scientist named Leo Baekeland managed to synthesize the first major thermosetting resin, and in doing so, he completely changed the trajectory of modern manufacturing.
That revolutionary material was named bakelite, right in his honor. Created through a condensation reaction of phenyl and formaldehyde, bakelite was the first true pioneer of thermosetting polymers. It became the tangible, real-world proof that we could actually engineer invisible chemistry to create materials with permanent, unyielding structures.
And this chemistry brilliantly illustrates why bakelite and the plastics that quickly followed it became so wildly popular. They are incredibly hard and rigid, highly resistant to heat and moisture, and act as fantastic electrical insulators. They also easily withstand exposure to harsh chemicals and organic solvents. Because of that 3D covalent web we talked about, these plastics are basically unfazed by the typical elements that would melt, dissolve, or destroy a standard thermoplastic.
And this invisible web builds right into the everyday engineering we rely on. Those incredible properties mean thermosetting plastics are the unsung heroes of safety in our homes. Because they are terrible conductors of heat and absolutely won't melt, they're the perfect material for the handles on our hot pots, pans, and kettles. Because they are excellent electrical insulators, they're used to make the internal components of our light switches, wall plugs, and even the cabinets for older electronics. They literally form a protective barrier between us and the dangerous heat and electricity required to run modern life.
However, every engineering marvel comes with a trade-off, right? As we reflect on what makes thermosets so incredibly strong, we also have to face their greatest limitation. Thermoplastics, because they can be melted and reshaped, can be reclaimed from waste. They're a working part of the recycling ecosystem. Thermosetting plastics, on the other hand, are insoluble, and their shapes are permanent. Once a bakelite handle or an electrical switch is formed, it cannot be melted down and turned into a new handle. It cannot be reclaimed from waste in the same way. The very chemical web that gives it its strength also seals its fate. Understanding this gives us a much more grounded appreciation for the materials all around us. When we reach for a hot pan or flick on a light switch, we are interacting with a permanent transformation. We're touching a moment in chemistry where a material was molded, locked into a 3D grid, and set forever to serve a specific, protective purpose in our built environment. It's a quiet, everyday miracle of engineering that, honestly, we rarely stop to think about.
So, I want to leave you with a quiet but vital question to think about. As we engineer our future, how do we balance our need for materials that act as permanent, unbreakable shields with a planet that desperately needs things to be remade and reused? The next time you grab the handle of a hot pan, take a second to appreciate the permanent chemical web protecting your hand, and ask yourself, what other invisible structures are holding our world together? Thanks so much for exploring with me today. Stay curious, and I'll see you in the next explainer.